Hello everyone, today this is our AERO Propulsion presentation. Today's topic is rotating detonation engine.
Rotating detonation engines are an advanced type of propulsion system which uses controlled detonations to generate thrust. Unlike traditional jet or rocket engines that rely on deflagration, a slower subsonic combustion process, RDEs use detonation. This supersonic combustion process releases energy much faster and much more efficiently, producing a shockwave that propagates around the engine in a continuous loop. This innovative approach creates much more thrust using less fuel, offering tremendous potential for aerospace applications, including rockets, hypersonic vehicles, and even naval ships. By achieving higher performance in a compact design, rotating detonation engines could redefine what's possible in propulsion technology. Rotating detonation engines, or RDEs, operate using a groundbreaking propulsion process based on detonation waves. In the engine's annular combustion chamber, fuel and oxidizer are injected through small openings and ignited, creating supersonic detonation waves that propagate in a circular path around the chamber. These waves are self-sustaining, they compress and heat the incoming reactants, triggering further detonations without the need for additional ignition sources. This continuous cycle can sustain anywhere between 2 to 5 detonation waves at once, traveling at speeds between Mach 3 and Mach 6, depending on the fuel mixture used, using a fuel-rich mixture for the higher pressures. What sets RDEs apart from traditional engines is the way they produce thrust. While conventional engines rely on slower, cyclical combustion processes, RDEs harness the immense energy of detonation to rapidly expand gases. This produces thrust more efficiently and compactly, making them ideal for advanced rockets, hypersonic aircraft, and even potential naval applications. The key to the success lies in maintaining the precise fuel oxidizer balance, which ensures stable detonation waves. This innovative approach to propulsion can significantly improve fuel efficiency and thrust-to-weight ratios, making a potential revolution in aerospace technology. Rotating detonation engines, or RDEs, bring significant advancements to propulsion systems, largely due to their unique detonation-based combustion process. Unlike traditional engines, which rely on slower deflagration, RDEs achieve rapid energy release through detonation waves. This efficiency is evident in the plot before us. The Jacob-Jacobs detonation cycle outperforms both the Humphrey and Brain cycles, producing more work from the same amount of fuel. The area above the Brain cycle represents this additional work. This advantage translates into higher thrust, using less fuel, reducing operating costs, and making propulsion systems more energy efficient. Additionally, RDEs eliminate the need for bulky compressors due to the high pressures generated naturally by detonation. This results in a compact engine design with fewer moving parts, which reduce maintenance requirements and overall system weight, critical for aerospace and defense applications. Furthermore, the supersonic detonation waves in RDEs lead to more complete combustion, maximizing energy output while improving thermal performance. This technology is also highly scalable, offering applications in not just rockets and aircraft, but potentially in power plants and naval vessels. RDEs promise a new era of efficient, powerful, and versatile propulsion, fundamentally reshaping aerospace technology. While rotating detonation engines offer exciting advantages, they also come with significant challenges that must be addressed before widespread adoption. One of the main technical hurdles lies in managing the extreme pressures and temperatures generated by supersonic detonation waves. These waves place immense stress on engine materials, causing rapid wear and tear. Additionally, the high pressure can result in backflow into the fuel and air injectors, requiring more complex and precise injector designs compared to traditional engines. Another challenge is maintaining stable detonation waves, especially when multiple waves are rotating simultaneously within the chamber. Combustion instabilities make it difficult to sustain continuous detonation, leading to potential performance inconsistencies. This instability is particularly critical as a precise timing of fuel injection is essential for stable operation. Developmental hurdles also include testing difficulties. Simulating real-world operating conditions in a controlled environment is highly complex, making it challenging to predict how RDEs will perform under varied loads and environments. Moreover, the wear and tear from supersonic shock waves further complicates long-term reliability while adding to the engineering challenges. While RDEs hold great promise, these disadvantages highlight the engineering breakthroughs needed to make them viable for practical applications in aerospace and beyond.
Now looking into the applications in aerospace of the rotating detonation engine, using the information before about the advantages and the challenges and the basic overall functionality of the rotating detonation engine, we'll look at real-life applications where this propulsion system would thrive in and why. So two designs proposed by AFRL, which is the Air Force Research Laboratory, which should compose of a rotating detonation engine, is the air-to-air missile. They propose this to have one based off their range increase due to the less weight and compact size of the propulsion system, meaning it could carry more fuel or it could also carry more armament. Another reason why they propose this is since the smaller size of the propulsion system, the whole missile can also decrease its size. So this allows it to be very compatible on a wide range of platforms. So now looking to the air-to-ground missile, they propose this to have a rotating detonation engine because of the range and loadout and payload would be enhanced due to the less weight and size of the propulsion system. So it can carry more explosives to effectively remove targets, similarly to the air-to-air missile. And going off on that point before, you can also increase the system speed while maintaining the same amount of payload, which is good for quick mission completion time. It is very similar to the air-to-air missile since it could be very compatible on a wide range of platforms due to this size decrease. One story that we found interesting was the impossible detonation. To give a little bit more explanation to this, in 2020, a group of researchers at the University of Central Florida and AFRL achieved what many thought was impossible, successfully demonstrating a working rotating detonation engine, powered by hydrogen and oxygen. This breakthrough came after decades of being unsure about whether such an engine could sustain continuous detonation waves. They used a small 3-inch copper test rig, and where the important changes occurred was when the team fine-tuned the fuel injection process to achieve the perfect mixture ratio of hydrogen and oxygen, allowing the detonation to sustain itself in a self-propagating wave traveling at 5 times the speed of sound. What we found remarkable is that just months prior, leading experts have publicly declared this concept unfeasible. Yet this success proved not only that detonation was possible, but rotating detonation engines could drastically improve fuel efficiency and thrust compared to traditional engines. This innovation has sent ripples across the aerospace industry, with the U.S. Air Force eyeing RDEs for potential use in next-generation rockets and hypersonic missiles, which we saw the AFRL propose before with the air-to-air missile and the air-to-air ground missile, based on the advantages of what this compact propulsion system can do.
Now that more information has been provided about the usefulness of the rotating detonation engine and its advantages in system performance, it is clear that this propulsion system offers significant benefits over the challenges. These include improved efficiency, reduced size due to its compact design, and its potential to lower overall costs in military applications based on the compact design. However, it is also important to acknowledge the challenges associated with implementing this technology, such as the complexity in operations due to the instability of detonations. Despite these challenges, we hope this explanation has demonstrated why RDEs require further research and exploration. Additionally, we want to emphasize that while progress in this field may seem difficult and complex, achieving breakthroughs is possible with perseverance and rigorous testing, as demonstrated by the challenges from the very first working experiment.